we got the correct amount, we couldn't get it to come out of the machine. Like it actually got stuck, because we actually use a tube. They got stuck, it stuck in the tube.
Come up.
So
All right. Where did it go? Did it just quit?
Shake the machine so it fall off. Yeah, today's a good day.
Okay. All right, so failure criteria. All semester, we have been figuring out how to determine the stresses in stuff if we push on it, pull on it, twist on it, do a combination of things. We figure out how much normal stress there is, we figure out how much shear stress there is, and once we know how much normal stress and shear stress, we are dealing with plane stress cases, and then we have to do what? Because we cannot add shears and normals. We have to, you have to do the transformation and find the principal stress values. Once we have those principal stress values, that's what we can use to apply different failure criteria. And failure criteria sounds like, okay, did it fall down? And if you remember back to part 2, when we talked about that bearing failure, that's an engineering failure, but it is not necessarily a structural failure. So the engineering definition of failure includes the fact that it deals with its yield strength. It doesn't necessarily deal with something falling down or something breaking. Brittle materials, on the other hand, chalk, concrete, different types of polymers, brittle failure often is a catastrophic, crack, pow, boom. So ductile materials, metals, is usually just if we get to this yield strength and a little bit of math. We're going to learn 3 different criteria today, one of which nobody ever really uses, but it's the simplest, and we'll establish the concept with that. And then there's these other 2, maximum shear stress and distortion energy, and those are 2 that people actually do really use in civil engineering codes or other design codes. So for mechanicals, the next course in the sequence is solid mechanics, 3624, and a very common thing in engines, in machinery of any type, is repetitive loading. You've got a drive shaft that rotates how many ever RPM, or you've got a bridge that has cars going over it how many squillions of times a week, or whatever. We're not dealing with that. We're dealing with one time only. We have a structure, we put a load on it, and we see how the structure reacts to a single static load. So we have to figure that out before we can figure out more complicated cases of repetitive loading or dynamic. It's different if I drop something. It's a very, very different case than if I just put it there. And so we're just doing the just put it there case. So the simplest criteria is the maximum principal stress criteria. So we do math, we figure out our reactions, we figure out our stresses, we figure out our principal stresses, and then we say, oh, is that principal stress bigger than the yield strength of the material? That's the maximum principal stress criteria. In terms of nomenclature, capital Y indicates the yield strength. Sometimes you see it as sigma y, sometimes you see it as a capital S. That's just saying it's the tensile strength. If you put a dog, what they call a dog bone sample, this particular shape, you put a dog bone sample in the instron, you pull on it, what's the yield strength? That's our sigma y, capital Y, or our S capital Y. And usually we are more interested in not just a yes or no. Are we at our yield strength? We want to know this ratio, this factor of safety. And that's the last piece of the puzzle, is this factor of safety. That's what you're going to code up in MATLAB tomorrow. And depending on the place, we either call it an FS or a lowercase n, depending on where, again, depending on nomenclature. So we take this and we multiply it by, what is this sigma 1? It's your largest principal stress. We do the Morse circle thing to find sigma A and sigma B, or I guess the way you're looking, sigma A and sigma B. And then we reorder and rank to get sigma 1, 2, 3. So your largest principal stress is sigma 1, and the ratio of the yield strength of the material and the largest principal stress is the factor of safety. If a material can handle 40,000 psi, and your loading situation has 40 psi, then you'd have a factor of safety of 10,000, or whatever that math is, 1,000. So that's factor of safety, but that's sigma 1, the biggest one is usually a tension. What if you've got a compression? Gesundheit. What if you've got a compressive case? So you can have a sigma 3 in a normal loading situation if you've not got hydrostatic pressure or hydrostatic vacuum. You're going to have one that's a plus and one that's a minus, and so you throw this negative sign in here so that factor of safety is always positive. So if you have a compressive stress, you just throw that negative, so the factor of safety in tension, factor of safety in compression, both positive. What does that look like if we plot it? We've had a few different plots, or we've at least had one new kind of plot. What are the axes on Moore's circle?
Normal stress and shear stress.
Normal and shear. That's the Moore's circle plot. We're going to look at one more new kind of plot today that is the principal stresses. Sigma A, sigma B. So looking at that allows us to basically, once you find the principal stresses and you put that point on a set of axes, you can look at your failure criteria and basically say, where is the limits of how big my principal stresses can be? So this is a graphical representation of the failure criteria. This maximum principal stress one is just saying, am I more than or less than? So that's why it's a constant in every direction. Just, did my tension get that big? Did my compression get that big? So it's a square. If your loading points of your principal stress are inside the box, that's a safe region. You do not expect failure. And more so, the ratio of these distances, just like Moore's circle allows you to geometrically figure out all these different things by what is the radius, what is the angle, you can do the same thing with factor of safety. That length divided by that length is the factor of safety. I mean, if you think about it, if this is halfway, then you could put twice as much loading. You would have a factor of safety of 2. So that square, that maximum principal stress one, that's the one that, okay, it's out there, but it's not really used in practice very much. Next one, max shear stress. It's called max shear stress, or it's called Tresca. And I mentioned before that things actually yield, back to 2070, these crystal slip planes and atomic lattice. It's dislocations in that lattice structure that cause things to skew or fail. And things skew or fail because of shear. Not because I'm pulling on it, but because they're being pushed sideways. And so this next criteria looks at the maximum shear stress, which we get from Moore's circle, and looks at how that compares to the yield strength in shear. The next couple of slides walks through how do I figure out what the shear yield strength is. We talked a second ago about this guy, S sub y. That's the plane tensile strength. And this is the one that's going to be commonly tabulated or Googled or whatever. It's the most common property you're going to find. But we're interested in the shear. That's what this extra S stands for here. The strength, yield strength in shear, or your tau subyield. Those two are the same thing. And so if we look at this and we say, okay, let's go back to the simple tensile test, because that's sort of the benchmark that we do. We take a simple dog bone sample and we put a load on it that gives you a stress equivalent to the tensile strength of the material. So you're taking it right to the breaking point. Let's draw Moore's circle for that. Moore's circle for that, what's the first point that I draw on Moore's circle? Is my sigma x and my shear. Well, for that case, I got nothing but sigma x. It's a pure loading case. So what do I plot? I plot that applied stress and 0. And then what's my sigma y? It was 0. So I plot 0 and 0. So this is Moore's circle for that simple uniaxial tension case where I'm applying S sub y. Well, what's tau max? It's half of that tensile yield strength, just by doing the Moore's circle problem. So that's tau max. So then the shear stress that I expect at the yield, my maximum shear stress, is the maximum, or is the yield shear value, which is half of the tensile yield value. Then any stress state is this factor of safety times what we've got and the strength. Well, we just said that this strength is half of the tensile strength, so here's our criteria. It's the regular tensile strength over 2 times the max shear. Just a little bit of algebra to get through that. And that's our new criteria in terms of the shear stress. If we try to plot that, this is where we get into this sigma 1, sigma 3, if they're different signs or if they're the same signs. If both sigma A and sigma B are positive, the maximum shear we learned is the biggest one minus the smallest one. So this is sort of skipping the sigma 1, 2, 3 step. But it's going through and saying, I can figure out what tau max is. I know that for my criteria, this is tau max. Set those equal to each other. Well, okay, your A equals the yield strength, which means it's just the straight line again. So if I plot that criteria, it's just like the first one. Did I get to that value or not? If they're different signs, if sigma A and sigma B are different signs, remember that tau max is different. Sigma 1 minus this value, but I still take tau max equal to the criteria tau max. And this guy now looks somewhat like y equals mx plus b. It's an equation of a line with what slope? It's a slope of 1 and an intercept of minus the yield strength. So it's a straight line. And then the same is going to be true if they're different signs. And the other way for the third quadrant, and you end up with this boundary that's a slightly different shape. It's the same as max principal stress in the first and third quadrants, but it's this straight line in 2 and 4. And so it's a much more conservative. Your factors of safety, if you're in the region where your sigma A and sigma B are different signs, sigma A positive, sigma B negative, it's much more conservative for a factor of safety. Okay, so that's Tresca. What do you do for Tresca? You figure out what the max shear stress is, and you multiply it by 2 to get factor of safety. So where did that go? It's the tensile yield over 2 times the max shear. That's that factor of safety. And all of these are summarized on 16 of your course pack. Yes, summarized on 16 of the course pack. All right, what's the last one? The last one is distortion energy. For this, we have one more new quantity, and that's a von Mises equivalent stress. It's again based on this fact that if you are applying hydrostatic pressure, what does that mean? It means the same in all directions. Either I'm putting something like in a hyperbaric chamber, pushing on it, or I'm blowing it up like a balloon. Those stresses do not tend to, or do not cause yield. And any arbitrary stress state, like you can resolve a vector into components in whatever direction you want, you can resolve a stress state into the part that's hydrostatic and the part that, this is this other word, deviatoric, meaning tending to cause skew. So you can have part of the stress just makes it smaller or bigger, and part of the stress tends to make it shift. And it's only that deviatoric part that causes failure, because again, you have to get the dislocations in the slip plane for the material to fail. All right, so that's sort of the explanation part. This is just kind of a fun piece of trivia. Hydrostatic pressure. Those are like normal styrofoam coffee cups that have simply been exposed to hydrostatic pressure, to 4,000 psi, and now they're itty-bitty little coffee cups. No deviatoric stress, they're still the same shape as they were. So the deviatoric part of it is the part, like I said, that causes the material to shift and ultimately fail. So that's just random, kind of fun. So how do we do the math? We need this von Mises equivalent stress. We can calculate the von Mises equivalent stress either by using, what are these guys? Principal stresses direct from Moore's circle, or we can use these guys. What are those guys? It's just the plain old arbitrary stress state that you end up with. Before you've transformed it, just at the end of your resultant stress problem, you end up with a sigma x, a sigma y, and a tau. Remember, we could end up with the porcupine cube. We could end up with all of those, but in here we're only ever going to end up with those. And so your sigma x, your sigma y, and your tau xy, your untransformed stress state, you can go directly into this formula and get a von Mises equivalent. In SolidWorks, when we did the stress concentration, you maybe remember that it was giving you a von Mises equivalent. That's what it had up there on the scale. This is what that means. It's giving you a transformed or an equivalent stress. So that's why it's report. And if you pull in SolidWorks, you can look at the X direction, or I think SolidWorks might call it IJK, but you can look at it in any of the 3 component directions, or you can look at the von Mises equivalent. And so you can do that either of these ways, and to get the factor of safety, you just take the tensile yield and take this guy and put it on the denominator, and that's your criteria. There, that's the semester. We're done. Those are the three failure criteria, so that really is the last new formula.
What's the end?
What's the N or what's the E and D?
What's the end? I just messed up.
So, 3 criteria. Max principal stress, am I bigger than the yield strength? Max shear stress, also known as Tresca, am I bigger than 2 times the max shear? Distortion energy, also known as von Mises, am I bigger than the von Mises stress? Those are the 3 failure criteria. I guess if you plot this distortion energy one, you get a nice ellipse. And the way that jives in with the other ones is it's kind of like the Goldilocks one. So this guy is not conservative enough. It's a fairly bad match for ductile materials in tension. Doesn't work very well. This guy is a little too conservative, but it's real easy to implement. I mean, find the max shear 2 times. This blue, this max shear one, is actually used in, I'm 99.9% sure it's used in the AISC, American Institute of Steel Construction codes that they actually use to say, yes, that's okay for the building. And this distortion energy one, like I say, it's the Goldilocks. It's the best fit. If you go test 10,000 samples and plunk the data on a sigma A, sigma B set of axes, you're going to get sort of this elliptical shape. So, an example, a quick, and I dislike really kind of going through PowerPoint, but okay, we have an example of shear only. So what is my stress state? My stress state looks like that. My sigma x is 0, tau x, or sigma y is 0, and the tau is the 10,000. Yield strength of the stuff is 40,000. How do I go through and do my criteria? You need your principal stresses because you need the maximum shear value to use the max shear criteria. So if I plot that, again, what's my first plot point? Is sigma x tau xy. And so that would be 0 and here. And what's my second one is sigma y, 0 and here. Then I draw a circle. And because this circle happens to be centered at the origin, then my 2 principal stresses are actually equal in magnitude to the shear. That's what that case happens to look like, a pure shear case. So sigma A is 10,000, sigma B is minus 10,000, and my max shear is 10,000. Lots of 10,000s floating around. What's sigma C? It's always 0. If I re-rank for sigma 1, 2, 3, This guy just slides up and becomes the middle value. And what's shear maximum is 1 minus 3 over 2. I need this to do the Tresca criteria, and I need this guy to do the von Mises criteria. I can do this either using sigma A's and B's or using sigma X, Y's, and tau. You will get to the same number. It's like going to Walmart down 10th Street or going around 264. You'll still get to Walmart. And if we put in numbers, we see maximum shear, which we already saw that from the plot, is 10. The von Mises is 17. And then what do I do to actually get the factors of safety? I divide. The numerator is the yield strength, the tensile yield strength. The denominator is the various different other quantities. And I get 4.0 for the maximum principal stress. I get 2 for the trapezoid polygon thing. And I get 2.3. Again, this guy's kind of the Goldilocks, just right in the middle, 3 bears, whatever I'm trying to say. And what does that look like on the plot? Again, this load line, like Moore's circle, the geometry works out that if you take this distance as a ratio of the distance out there, you can see that that's halfway, that's a little more, and that's times 4. So the geometry of it works out. And I think I've kind of already said that they differ most in pure shear. I mean, yeah, if you had both principal stress is positive, the blue line and the red line, it's the same criteria. They're not really different in the first and third quadrants. So that's it. I would like to work through, I'm going to skip to the steel tube problem that is on 6-18. So this is an example of something that I'm looking for in terms of the scope. This is a sample problem of the combined loading. This fits for the combined loading project in terms of having multiple stress resultants and going through the whole process to end up with the factors of safety, because that's the end point of what is the factor of safety of this structure that you've picked to analyze. So if we go to this one, is that it? No. Yep, there it is. All right, page break. So, and I've got some workspace over here. So, we have this scenario. We have a pipe connected to the wall by a flange, and we know that it's 2 inches outer diameter and the wall thickness is 1/4, and we're going to put 500 pounds coming down from here. And our instructions say draw Moore's circle for the critical stress state, which we have to figure out how to identify which state is the critical stress state. We say yield strength is 60,000, and find the factor of safety using max shear and von Mises. Dimensions are in inches. All right, so what's going on? What kind of stresses are we going to get from this loading scenario? We got torsion going on for sure. We've got normal stress from the bending, and there is also the shear. Now, again, the caveat is usually that shear is negligible if that shear value is small compared to the resultant moments, and we'll do the math to make sure. Where is going to be that piece of material that we expect to be the problem piece? Where is our maximum critical stress state? It's cantilever, so it's going to be back here at the connection point. And with the way this is loaded, do we know if it's top or bottom or side? Do we know that yet, or do we need to think about that? We might need to think about that a little bit. If you've got bending, where does your max normal stress happen? It's a symmetric cross section. So normal stress, because of bending, where is the maximum? Top and bottom. One's tension, one's compression. Okay? What about my torsional? It's the same all the way around. So it's pointed, if we go this way, you've got some going this way, you got some going that way, you got underneath, and you got up. But those can't add directly with the normal stresses because those are shear stresses. We have to figure out the principles. And the shear would do what? The shear is just going downward. So basically, it's either going to be the top or the bottom. How do I know that? Can you explain to me why I know it's the top and the bottom, not the left or the right? Well, it comes back to the fact that, again, or let me say, if this shear is negligible, it's going to be the top or the bottom. If the shear is negligible, it's the top or the bottom. Because this shear force acts the same on both sides. Different circle. The shear stresses from the torsion do this. The shear stresses from the linear force do that. So if the shear is not negligible, it'll be here at 3 o'clock. But we know what is the shear force. We know it's 500 pounds. How much are the moment arms? They're bigger than an inch. So just looking at it, you can see that those resultant moments are going to be thousands, not hundreds. So just rough order of magnitude, you know that that V term is going to be down in the noise. So we can say we're not going to deal with the shears. But what's the picture of the resultants? So being a little more diligent, we know we are going to have a shear force, and it would be V equals 500. What else do we need? And this is back here at point A, at the connection point. So what else do we know? We know we have bending moment. We have bending moment like this. What is the moment arm for that bending moment? Is it the 9 or is it the 15 for the bending moment? It's the 15. So that's 500 times 15. And then we have a torsional moment like that. And if you have downloaded the filled in version, my arrow is drawn wrong in the course pack completed ones. The arrows are pointing the right way, but this arrow is pointed the wrong direction. So that is 500 times 9. So that is 7,500 inch-pounds, and that is 4,500 inch-pounds. All right. What kind of stress do I get from this? I need to figure out what my stress state is. How do I get bending stress, Cassiolo? What kind of stress is it?
I know it, but it's not in the game right now.
Is it normal or shear?
It's normal.
It is.
it's my over I.
It is. It is my over I. This is symmetric, so I can just say plus or minus mc over I, the more general. All right, what's my C? This was a outer diameter of 2 inches and wall thickness of 1/4. It's 1 inch. It's the distance from the neutral axis in the middle out to the furthest point. So this guy is plus or minus 7,500 times an inch over, we need that guy. Well, he's pi over 64 OD to the 4th, ID to the 4th. And we're given all that, so that ends up being 13,969 PSI. That's my normal stress. All right, what else we got going on? We got a torque. So from bending, from torque. Brogdon? You were trying to hide there for a second. What kind of stress? Normal or shear? Yeah. I almost have to yell at Stephanie. TC over J. And so that's 4,500 times 1. Why is that C is the same? The radial distance, but it's a round cross section. It's still the distance from the center to the outside. And J is pi over 32 times the same stuff. And that ends up being 4191 PSI. From shear, I'm just going to reiterate that shear is 0 at the top and bottom, where sigma is max. If you had a very short moment arm and a very large force, that V becomes significant. Very short moment arm, very short beam, very large force, you start not being able to ignore the V. So, like, when would that be? Like, I don't know, these high-rise buildings that have the concrete decking that's sort of just cantilevered off as a plate off of the wall. That is an issue where it is a significant load. It's short compared to the amount of load. So that's an issue where that shear can become significant because it's a relatively large force and a relatively short moment arm with that distributed load. But it's negligible here. Oh, stop with the spinny circle. All right. So now we need to know, what does the stress state look like? We know that we have 1369, and it's tension at the top, compression at the bottom. So if I come
over here and let's go for red. And I think about a little hunk of material right there at the top. And I've got my little hunk of material up here.
physically, which way would my, yep.
Don't we do the DQ or IT part?
No, that's what I'm saying. We're ignoring that.
Okay.
Because that V is negligible because the moment arm is long. If you do it, where in the cross section is the maximum?
And left or right side?
Right. So, yeah. It's where there is no normal stress. So, All right, so at this top, this is at point A. We would have normal stress coming out from the surface. And we also have shear stress going which way? We're twisting it like this, so my shear stress on that cut surface needs to go that way, which means I also have one going back that way. Okay, if I instead look at a section underneath at 6 o'clock, what is that one going to look like? What's different? It's compressive, and these values are what? 13,969 and 4191. Okay, so I would have 13,969 into the surface, and I would have shear going the other way. Is everybody cool with how I ended up with that drawing?
So you said this one for the top one is at
It's at noon.
At noon essentially. Okay.
Yep.
And the other one's at the bottom.
And this one's at 6 p.m. And we're ignoring 3 and 9, again, because we've said that V is negligible and sigma is 0 there. Or if we drew it, it would look like this. We would have a 4191 and some unknown value from the shear V. We would have a VQ over IT. And on this side, it would be 4191 and a VQ over IT. But it would be a pure shear state. There is no normal stress at those two.
So when we're analyzing for combined loading, we have to figure out where the max normal stress is, and then go from there. Like, if there is no normal stress at a location, it is just considered to be negligible.
I would do, if you have any question as to whether this is negligible, go ahead and calculate VQ over IT. And then you would have 4 stress states that you would then find the principal stresses for. Because what do we do from here? From these, we now draw our arbitrary stress state. So like at noon, what is that then going to look like? It now looks like this. This is my sigma x, because the x direction is along the beam. So 13,969. How much is my sigma y? I got nothing. Sigma y equals 0. How much is my shear? 4191. Okay. If I drew a stress state, so this is at noon. If I drew a stress state for 3 o'clock, what would it look like? It would look like 2 of them adding in the same direction, one of them being 4191 and one of them being VQ over IT. You can then now take these stress states and do Moore's circle and figure out your principal stresses. And I can guarantee in this case, the sigma A and sigma B here would be way less than the sigma A and sigma B from noon. That's why I know I can ignore 3 o'clock and 9 o'clock. If you have a very short beam, if you have a simply supported beam instead of a cantilever, it depends on your case. You should calculate the principal stresses for noon, 3, 6, and 9 just to say, oh, okay, it is 3 o'clock that's worse. And then you do your factor of safety analysis on the one where the principal stresses are the largest. In our case, our sigma A and B are going to end up being equal for noon or 6. So, and I'm kind of out of time, so I'll talk fast. So this is our principal stress state. What do we do from here? We do Moore's circle. I'm going to skip the drawing of the Moore's circle part. You guys are good with the actual drawing of it. So what do we need? We need to figure out our sigma A and sigma B. And what is that? That's the sigma average, which I trust that you can get, plus the radius. This guy is sigma average minus the radius. And it ends up that these numbers, if I jump to the end, are 5, that's not it, 130, and minus 1161. Now I need to do my failure criteria. Which two did I want to do? I wanted to do, oh wait, I'm not quite done. What's sigma C? Now I need my sigma 1, sigma 2, sigma 3 because I'm doing the max shear criteria, so I need to figure out my max shear. How do I get my max shear? Sigma 1 minus sigma 3 over 2. And so what is this? This is 15,130. This is 0. This is minus 1161. So this guy is 15,130 plus 1161 over 2, 8145. Now, for the actual criteria, max, this is from the page on 16 is the formulas, max shear failure criteria. What's my formula for factor of safety for that one? Max shear or Tresca criteria. What do I need? FS equals yield strength over 2 times the max shear. What's the yield strength? It was given in the problem statement as 60,000. What was tau max? That was what we just figured out, 8145. So that ends up being 3.68. Okay, what's my other criteria? My other criteria is this distortion energy, or von Mises, which means I need sigma prime. I need my von Mises stress. I can either use sigma A's and B's, or I can use sigma XY tau. I'm going to choose to do the sigma X version. Why? What's sigma Y? It's 0. Goes away, goes away. So that is 13,969 squared plus 3 times 4191 squared. Sigma prime is 15743. And how do I get my factor of safety with distortion energy? It is just the yield strength over that von Mises stress. 60,000 over that number is 3.81. And there you have it. That's your factor of safety. And that right there, that process from going from a structure that has loading to the stress state, to the principal stresses, to the factor of safety, that's what we've been aiming for since August.
Couldn't do that one first day.
We could have. And y'all would have been so confused.
Yeah, we probably never came back.
Yeah, it's been a lot of alphabet soup to get here. One thing I really like about this class is it really is all one thing. Like in fluids, it seems like you learn a little bit about this and then a little bit about that, and it's not necessarily all connected. But yeah.
Course back is key.
You like that?
How'd that go?
Oh, we're pretty good.
Yeah. Are you going to go out there this summer?
They